So we need to record it.
No, okay. Why did you turn it off? Okay. So then you can use it to perform performance precision tuning. So we did a little bit of that. And then, it can help you to find parts of the code where you maybe have to apply error compensation. So, you find routines that cause a lot of error on the output, and you go in there and you hand tune them to bring the error down. And finally, you can do kind of like equivalence checking between two implementations of the same routine. And you can see whether, how their error profiles look like, and whether, they're the same or not, and so on. Okay. So we devised a static analysis that over approximates the computes a bound on the error on the output of a floating point routine. So we are not the first ones to do this. There has been quite a lot of work in this area before us. But we kind of distinguish ourselves from this related work in a couple of important ways. So our approach handles nonlinear and transcendental functions. And then we show that we provide tighter upper bounds than previous work. And there's some good reasons for that. Also, our whole tool flow is rigorous. So we know that the bound that we provide is going to indeed be an over approximation. And we implement this in a tool. It's available on GitHub, and you can download it and play with this. So the tool is called FPTuner, and this is the tool flow. So on the input, as an input, it takes a floating point expression and intervals of its over its input variables. And then from that, it obtains so-called symbolic Taylor form. And I'll show you what I mean by that. Then from that, we generate our error function, and we use a global optimizer to maximize the error, to find the maximum error that we could have on the output. As a side project, we can also generate whole light certificates to make sure that what we produce is indeed an over approximation. And so now I move on to the kind of the technical part of FPTuner that presents how we obtain the symbolic Taylor forms, and what is the error function, and so on, and why it scales, and why it provides a good estimate. Okay, so based on the standard, people have defined this well-known rounding model for floating points. And other people use this in their work as well. So if you have an operation over x, y, where x and y are floating point values, and operation is a function that returns reals, then round-off errors are captured by this expression. So you perform your operation over reals, and then this adds this error, floating point error noise, to the result of the operation. So this E is error that gets introduced. And then there's this special part for subnormal values, but I'll ignore this in the rest of the talk. We'll just focus on this part. And based on the standard, these guys are bounded by constants. So for single precision, this E can be at most 2 to the power of minus 24. For double precision, 2 to the power of minus 53. So it depends on the number of bits you have in your mantissa. Okay, so you can represent each floating point operation using this, and this is over reals. And this is what introduces the error. This models the floating point error. So let's look at an example. So we have this simple computation. X is divided by x plus y. So now, if we plug in the model, this is the expression we get. So this is the expression that captures the floating point error that you can have on the output. And we have to introduce one E per operation, and these E's are bounded by this constant that I showed on the previous slides, and these constants are called machine epsilon. And then the absolute rounding error is just this expression minus the original expression is over reals. So our goal is to maximize, to find out what is the maximum of this absolute rounding error. So what is a simple way to do it? Well, you can try to maximize this. Your input variables will be x and y, and E1 and E2. So, and that's the actually first approach we tried. You can kind of encode this in an SMT solver that supports nonlinear reals. You can build a little binary search around it, and you can actually find these maximal errors. Now the problem with this is that it introduces 1 E per floating point operation. So as the routine grows larger, even though the number of inputs is small, the number of these inputs, the number of E's is going to be linear in the size of the code. And the decision procedure really doesn't like a lot of inputs, a lot of variables. So it chokes the solver really fast. We just couldn't make it scale. And so we started thinking about this more, and we realized, okay, we want to try to get rid of this dependency on the code size. And that's where symbolic Taylor expansion comes into play. So we use it to reduce the dimensionality of the optimization problem. And the basic idea is that we treat each of these little E's as noise variables, and then we expand based on the Taylor theorem. We keep our coefficients, x and y and so on, symbolic. And then these coefficients are going to weigh the noise, and they're going to be correlated and so on. And once we do that, then we can again apply global optimization, but now the problem is reduced. To be able to do this rigorously, we actually had to develop our own global optimizer called GELPIA, because everything we could kind of find out there wasn't really rigorous. It was actually using floating points under the hood and had floating point errors of its own, and so the results, we could not really make sure that the results are rigorous. So if you're interested in this area, there is also a global optimizer that provides rigorous results that you can download and so on and play with. And we support nonlinear, linear, and transcendental functions quite easily in this framework. Okay, coming back to our example, let's see how do Taylor forms look like. So this is our function that captures the error, and when we perform Taylor expansion, it expands into this. So this M2 here summarizes the second and higher order error terms. This number is going to be really tiny, and so we can perform some simple analysis on M2 to overestimate it. It's not going to influence the overall result a lot, so we don't have to worry about it too much. And then if we kind of play with this expression a little bit more, we can derive that the floating point error is then bounded by this expression. So we put absolute values around these guys, and then we plug in these constants around E. So this over approximates the absolute error. And then in the next step, we can compute these derivatives, or symbolically compute them, and then we can use the global optimization to find their maximums. So if we do the first one, we get x over x plus y. We give this to a global optimizer, and we get its upper bound, u1, and we can plug these bounds in this expression, and then we'll get the overall bound on the error. Another thing that I want to note is that when we do this, it's really easy to switch between different floating point types, because the only thing we have to switch are these constants. So if you want to analyze a routine that uses single precision versus double precision, it's just simple change of this machine epsilons, of these constants. So this is kind of technical part behind the tool. Any questions about this before I move on to some results and some other stuff? Yes?
So for when you say global optimization, is the problem convex? So that's the guarantee of...
No. No. That's the problem. No, it's very irregular, so we couldn't use any of the usual tricks that you can use to optimize. So it's a branch and bound based optimizer and kind of brute force, let's say. We use some tricks to try to prune away the search space, which make it scale, but yeah, it's a kind of pretty regular function. Yes. Yes.
Is the Taylor expansion always done around 0, or are you also choosing some other points?
Around 0. It's kind of the most convenient one for us. Yes.
Is that better suited than for the relative error, it seems to me, than for the absolute error?
Yeah, I'm not sure about that. Yeah, usually we do it around 0. Yes. Any other questions?
You always use the expansion of degree 2, or are there scenarios where you allow higher order terms to capture more, or you need to allow more higher order terms?
Yeah, so that's a good question. So we've never seen that we would need such higher precision. Like second order term is already like orders of magnitude smaller than the first order one. So yeah, so far we haven't really seen the need to go beyond this. Yeah. Okay. So I have one example result where we actually try to visualize what is happening when we run FPTuner on example. So there is a set of benchmarks that is maintained by a bunch of guys from UW. It's called FP Bench, and this is one of the benchmarks from this benchmark suite called JETENGINE. And these two graphs are showing the actual results we obtained using testing. So you can measure errors using testing as well. If your input size is small, and we kind of made sure that's what we worked here. And then this kind of pink red line is what FPTuner gives us. So remember, this is FPTuner does it statically, and it's an over-approximation. And you want to make sure, of course, that your over-approximation is not really bad. And if you look at this, you can see that FPTuner kind of follows the actual error results pretty well, which means it over-approximates the error nice and tight. So that's what this graph illustrates. Okay, to summarize this part, so we devised this new method for rigorously estimating floating point runoff errors, and we implemented this tool called FPTuner. And look at the papers. FPTuner performs pretty well, and it beats a bunch of other tools in terms of how tight its error bounds are. Okay, so that's the analysis part. Yes.
So how tight are the error results with static approximation to the input intervals that you need to give?
Could you repeat this? How tight they are?
You need to provide input intervals for every variable, right?
Yes.
So let's say I give coarser intervals.
Are
they still reasonable, good over approximations that you get from the FPTuner?
Yeah. Once you start, well, okay, first we might run into performance issues. Because once so that's one thing, because when we run Global Optimizer, we kind of have to search over this input space, and if the input space is really big, we might choke in the Global Optimizer. The other thing is, as you're kind of making your input intervals larger and larger, usually we hit one of these corner cases that leads to really big errors. And so you will hit one of these spikes. So we will still over-approximate it pretty well, but you'll just get really large error. So that's kind of the problem, yeah. Good question, though. Any other questions? Okay. Okay, so as we've seen in other talks, and as you can imagine, once we have analysis, we can also start playing with synthesis. And so we did a little bit of that as well. In particular, we devised this technique for what we call mixed precision tuning. So what does that mean? So given an expression over reals and some kind of user-provided bound that on the error that we can allow on the output, we can automatically synthesize precision in terms of floating points or for all operations and variables in this expression to satisfy this error bound. Okay, so how do we do this? We already hinted at this in the end of the analysis part of the talk. We have this machine epsilons, and in FPTailer it's pretty easy to play with different machine epsilons to see what kind of errors you get on the output. So in this work, we replace them with symbolic variables. So instead of fixing it, we say, no, this S1 can be either single precision or double precision. And then we do the same thing for S2. And now we have another optimization problem. We want to compute allocations for these precisions that satisfy the error bound, while at the same time, trying to stick to, let's say, the lowest precision possible. So we have some kind of cost model for this. And that's what we implemented in a tool called FPTuner. So what is a TOOLFLOW FPTuner? So as input, it takes a real valued expression. And then this is kind of the FPTailer level. So we use FPTailer to generate the error model. And we have some model for efficiency, performance, and so on. So we don't like to do casts, for example, because they're costly and things like that. And we find the error bounds using this GLPI global optimizer. And then we move to the second layer of optimization, where we use Gurobi to find assignments to these precisions. And in the end, we get optimal mixed precision allocation that satisfies the error bound. And then users can also provide error threshold and kind of weights of the operators, how much each operator costs, and so on, to make this, let's say, more realistic. Okay, so we did a bunch of experiments using FPTuner. I won't have time really to go into the details here. Lots of it is in the paper. Here's just one example. We took a small Jacobi example, and we enrolled it, and then we tried to infer precision of all the operators to satisfy this error bound. And as you can see, you can get kind of a mix here. Different colors represent different precisions. And then there is a bunch of similar examples in the paper. Okay, so to summarize the synthesis part, so we developed a synthesis tool that supports mixed precision allocation. It's based on FPTailer. It means everything is rigorous, and we actually provide a proof that it satisfies the given error bound. We encode this as an optimization problem, and we did an extensive empirical evaluation, including actually measuring how much energy gets used when you optimize using FPTuner and so on, using wattmeters and things like that. So students had a lot of fun doing this. Okay, any questions about the synthesis part? Okay. Okay. So the last thing I want to talk about, so this is pretty much an ongoing work that we are still kind of improving and so on. And it's on a decision procedure for solving floating point constraints that is based on search. Okay, so we've been working in this area for quite some time now, and we certainly noticed that decision procedures for the theory of floating points are still kind of quite slow and not really scalable. There is a bunch of solvers now that support them, including Z3, MATSAT, and so on, but they're not very scalable. Often you can solve just really tiny formulas. So recently we kind of started looking into this, and we've been trying to devise better decision procedures for this theory. So in particular, there are previous results that showed that the solving based on search can be effective for various other SMT theories, like, for example, bit vectors. Because they perform the search directly on the theory level, and sometimes search is just faster than doing bit blasting. Of course, it is not complete. You can't really prove that something is unsat. You're just trying to find models, right? But often, you can find models really efficiently. And so our research question was, can we achieve similar efficiency if we use stochastic local search to solve formulas in the theory of floating points? And this work was inspired by some similar results that were implemented in Z3 that do this for the theory of bit vectors. So if you think about stochastic local search, it's a pretty simple algorithm. Well, you perform some local search plus random choices along the way to find your minimum. And what are the key ingredients? Well, you need a score function to figure out what is the best next step to perform. You need to define a neighborhood relation, which kind of helps you to decide in which direction to move. And then, you can also throw in a bunch of heuristics to actually make this performant. So I'll talk about each of these ingredients in more detail next. Okay, first the score function. So our score function is computed based on the current assignment that we have to variables in our constraints. And it takes the assignment and the constraints, and it returns a rational. And the intuition behind the score function is that it tries to encode the degree of, let's say, satisfiability, of the current satisfiability of the expression over the constraints. So, if it's 1, then the constraints are satisfiable. And if it's not 1, where they're not, but the closer you are to 1, the more satisfiable they should be. So this is kind of a simple example. If your constraint is x greater than 2, and currently in your assignment 1.99 is assigned to x, that should have a greater score than the same constraint where x is assigned 0, because you're kind of closer to satisfying it. And of course, this is kind of heuristics. Like, you can't do this all the time, but it's heuristics that we use. So our key idea here is that we define the score function by measuring the distance between signed ordinal indices of two floats. What are signed ordinal indices? Well, they just ensure that there is a total order of floats, and the neighboring floats have a distance of 1. So it's kind of turning floats, let's say, into some kind of ordered integers. And we don't just use, distances just between computing distance between two floats as a score, because then, two floats, if you remember the line, the number line for floats, even though two floats are neighbors, when your exponents are large, their distance is going to be very large. So that's why we want to avoid this. By doing this, we get rid of that. So that's our score function. What about neighborhood relation? Well, this is also kind of inspired by what they do in Z3 for bit vectors. So there, the mutations there allow our bit flipping. In our floating point work, we also do some things that are floating point specific, such as changing the unit in the last place, or changing the exponents by dividing the floating point number by 2 or multiplying it by 2. So that's how we kind of move in our search space. And then we added a couple of heuristics that we find work really well. So the first one is that we try to remove equality constraints whenever possible. As you can imagine, when you're doing search, equality constraints are kind of hard to satisfy. Inequalities are easier. Also, we bootstrap our search by using a model that we obtained by solving the formula using the theory of reals. So that's a common trick that other people are using as well. And then in terms of how we search for the best neighbor, that can often be costly, and so we do it in a couple of stages. We first search neighbors that are moving you the most, and then closer neighbors and closer neighbors. So those are the three tricks that we do to make this performant. Any questions so far? Okay, yes?
You have a floating point number, you treat it as a bit pattern. So then your score function is just treating an integer distance between two numbers, right?
Yeah, you have to be a little bit careful about negative numbers. But that's basically it, yes. Yeah. Anything else? Okay. So the main thing that matters in this space is, of course, the evaluation. I mean, it's all about being faster and more scalable than other tools out there. So we did a pretty extensive emulation of the prototype tool that implements this. So we compared our tool with a number of other ones that support solving formulas in the theory of floating points. So there is CVC4 and Z3 that do bit blasting. Matza does some kind of hybrid solving. And JFS is also based on search. Actually, this tool was done by Ali, who presented yesterday, and some of his students. And Colibri is based on constraint propagation. It's a very kind of recent tool. So here are the results. Let's focus on Oliver H. So that's the one that turns on all the heuristics. Oliver B is Oliver without, and Oliver is the name of our tool. Oliver B is Oliver without heuristics. So in terms of the number of benchmarks for which it returns SAT, it can solve the highest number of satisfiable benchmarks. So more than any other tool. Matzat is pretty close and so on, but we are still, a little bit better. So know that this is a couple of months old. So my student has a bunch of ideas how to improve this. We will see how this goes. But these results were really encouraging to see. Okay, we can skip this. I would say, kind of more mature tools in this space are Z3 and JFS. And when compared to them, so this column shows how many benchmarks are solved by Oliver, but not by these tools. So this means that Oliver can solve all the benchmarks that Z3 and JFS can solve. And on top of that, it solves 43 more benchmarks than Z3 and 20 more benchmarks than JFS. So, when I saw this table, it's really encouraging, and I will continue working on this and then try to improve it further. Okay. Okay, so to summarize this part, so we implemented this prototype tool called Oliver for solving floating point constraints using stochastic local search. We devised these key ingredients of the search algorithm and a couple of custom heuristics that work pretty well in practice. And we compared the tool to a bunch of solvers that are currently available, and we showed that it's already effective. And another interesting thing about this work is, so it was done by kind of a PhD student that was close to graduating, and I totally was telling him, like, don't do it. There is no way you'll be faster than all these other guys who have been working on this for a couple of years and so on. Like, it's a risky project, don't do it. And he still went ahead over summer and kind of implemented it, and he brought me the results, and he was like, oh, there we go. I'm actually already faster than these other tools. So this was really nice to see. Thank you. I'll conclude my talk here.
Thank you. Any more questions? So could you maybe say a few words about how you integrated this into like an existing SMT solver, or maybe even a tool like Boogie or Viper to let people make use of it? Yeah, currently this is just a prototype. It's not integrated anywhere. I mean, it supports the SMT-lib format for the theory of floating points. So you can speed it out and then run our tool on it. It's available on GitHub and so on. Mm-hmm. Yeah, we are thinking about integrating it into Z3, but we still didn't get there.
Currently, it's a self-setting tool.
Okay. And do you have any experience about the interaction between the float theory and other theories?
Yeah, it's horrible. I mean, our kind of SMT solver of choice is Z3. And typically the theories we use are arrays. Well, we almost always need arrays when we do solve verification. So we definitely see that combining arrays and floating points is just really slow. Mm-hmm. In fact, arrays and bit vectors is, again, also pretty slow. And we still have to, I mean, now Z3 has these tactics, right, that you can kind of use. And apparently, I mean, this is all word of mouth, right? You talk to people. If you actually compile away arrays kind of a priori before handing it over to the theory solver, it works faster than by doing theory combination. Mm-hmm. So one thing to try if you're using D3 would be get rid of arrays and then just use the theory of floating points. But we still haven't tried that. Yeah.
All right. Any other questions? Yeah.
So yeah, that's maybe a bit out of scope, but are there other proposals, or do you have one to represent floats to make it easier to verify them, more predictable to work with?
I'm not sure what do you mean represent floats? Use some other format, not floats?
Some other, well, yeah, exactly, yeah, some other format to represent reals, I should maybe say, yeah.
Ah, yes, so we kind of played a little bit with fixed point arithmetic, which is another way to represent reals. People do it a lot in kind of embedded systems, and also these days in neural networks, machine learning, and so on. I would say maybe it's even used more than floats. So that makes it a little bit, I think, easier to verify because, well, they're just kind of integers. You have to be a little bit careful about overflows and so on. So I think that's kind of an interesting space to take a look at. We worked on it a little bit, but we still don't have anything kind of more concrete. Yeah.
Okay, so thanks again.
Thank you.
Okay, so we have a coffee break for like 25 minutes.